Good afternoon or good morning, good evening to everybody. So this is the third lecture today, and I will just to maybe I should start basically with the general outline that I had. So at the moment I'm still so that's what we covered during the first two lectures. This was an introduction to random matrix theory. And the goal of today is basically to show you to go to another problem, which are fermions. I already mentioned fermions several times during these lectures. And what I want to really show you is the connections to a random matrix theory. So I think this sheds light a bit on how to understand and interpret the correlations that people have observed in the random matrix theory and that we have been discussing up to now. So I really need to start somehow a new subject, but nevertheless, I will just make a short recap on what we have seen up to now and what are the main things that I will need in the following. Okay, so this is to remind you that we have mainly studied this Gaussian orthogonal and unitary ensemble of random matrices. And there we have discussed at length the joint distribution of the eigenvalues, which can be written in this way here, okay? And in particular, we have seen that there is this exponent beta with beta equals 1 for GOE, beta equals 2 for GUE. And we started to investigate some properties that can be extracted from this joint distribution. Of course, in general, it's quite complicated because of this term, which really couples in a non-trivial way the different eigenvalues, which up to now, I told you one can see them as the positions of a gas of interacting particles, if you want, via these logarithmic interactions. And we started to investigate the most natural observable that you might think of, which is this the density of particles. And we have seen that in a large n limit, this rho n of lambda goes to a limiting distribution, which is the Wigner semicircle, SC semicircle, and which quite remarkably has this finite support between minus square root of 2 and plus square root of 2. And this is here a sketch of this density here. So this should be a semicircle here. And one important point that I discussed is that there are essentially two distinct regimes when you look at local correlations in this model. One, which we usually call the bulk, which means roughly speaking the center, or close to zero or not too close to the edges. So that's the bulk part. And the second regime is really what happens close to this, close to the edge, and this is called the edge regime. Of course, there are two of them in this case by symmetry, the right edge and the left edge, but they behave just in a similar way. And so that's really what something that you have to keep in mind because we will come back to that later on. Okay, so that's the main messages probably that you have to have in mind right now. And we will, of course, encounter soon these people again. But for a while, we will just focus on a different problem, which has to deal with fermions, non-interacting fermions to be more precise, and their connections to random matrix theory. Okay, so let's start with the model that we are looking at. So it's a very simple model actually. So I will just consider n fermions, and I will forget about their spin. So in a sense, I will not. The spin, of course, will play a very important role concerning the statistics of these fermions, in the sense that their wave function will have to be antisymmetric. But I will imagine that I have imposed an external magnetic field such that all the the fermions are projected in the same spin state, okay, say all up state, if you wish. And I will just look at these fermions. So n spinless fermions without interactions. So that's and what is important is that I will put them in a trap, in a 1D harmonic trap. That's quite simple in principle. Okay, so that means what? So that means that again, typically, no, I mean, I will have this. So that will be my potential V of x. That will be just of that type. So other simple model, okay? And I want to understand what happens when I put fermions in this model, okay? In this trap, okay? So that means that basically I will have a full Hamiltonian, which will be the sum of single particle Hamiltonian h hat of I, and each h hat of I basically this is just pi squared over 2m plus this potential v of xi. Okay, so that's very simple. And of course, the first thing that I need to understand is or are the eigenstates of this single particle Hamiltonian. Okay, so that's a textbook problem, but let's just proceed and write explicitly the single particle eigenfunctions. So as you know, you can build them in a very easy way. So let's put some color just to. So they are labeled by an integer k, and up to a normalization constant, they are just the product of a Gaussian. So I need to define what alpha is. Alpha is just it's basically an proportional proportional to the inverse of a length associated to the trapping potential. And the non-trivial part is that this is just the product of this Gaussian times a Hermite polynomial of alpha x. Okay. So I have here k. So I chose this. Numbering here. So I have the index k minus 1, and k. That means that k basically starts at 1, 2, etc. And of course, the associated eigenvalues epsilon k. I just because of the numbering that I chose is slightly different from what you have. Usually it's just k minus half, okay, because I started at k equals 1. Okay, so the ground state is k equals 1. This is usually k equals 0. I mean, standard textbook, but for you will see why this is just for notational convenience. So what happens there? I mean, as you know, right, is that okay? You have the first level here, and then you will have your second level, and then you will have the third level, and so on and so forth. Okay, so I would have here k equals 1, k equals 2, k equals 3, etc., etc. Okay. So this is for the single particle Hamiltonian and single particle associated wave functions. Now these HKs, as I said, are Hermite polynomials. Okay, so and they are of degree k. So if I look at h, for instance, h0 of x is just 1. H1 of x is simply 2x, for instance. H3 of x, sorry, H2 of x is simply 4x squared minus 2, and so on and so forth. Okay. So now this is quite easy, of course. So now let's put let's look at what happens when I have n fermions. Okay. So I will first focus on the 0 temperature case. Okay. So I will mainly be interested for now into the ground state. Okay. So I just focus on the t equals 0 limit. So I want to understand the ground state of this problem. Okay. So what happens when you look at the ground state, of course, because they are fermions and spinless fermions, I put my first fermions here on the ground state. The second fermion will be there. The third fermion will be here. And the fourth fermions will be somewhere there. And at some point, I will have the nth level where I will put my, so I have level n here, and I will just put my nth fermion there. Okay, so that's the way I will minimize the energy of the system, obviously. And now from it, I want to write the n particle wave function. Well, I mean, the main, so this is what I will denote by, say, psi 0 of x1, x2, xn. And what we know is that it has to satisfy it has to be an eigenstate of capital H. And on top of that, it has to be completely antisymmetric with respect to the permutation of any of the xi and xj's, okay? And the way to construct that, I mean, again, this is a standard textbook result. This is what is called a Slater determinant, okay? So basically, I will just construct it as a determinant that I will build from these single particle eigenstates, okay? And here I have n particles, so the indices k and l just go between 1 and n, and that's why actually I use this this thing here, okay? Because if I started from 0, then I would be a bit that would be a bit a pity here to have an index for the matrix which starts at 0. So that was just the trick here. Now, so what you need to do now is basically to insert this expression here into this determinant. So let's try to manipulate a little bit this determinant. There is one thing that you can easily do is that, okay, so there will be some prefactors there that I can just get out from the determinant. And also, I mean, I can simply use the multilinearity of the determinant to get rid of these Gaussian factors and just put these Gaussians outside. Okay, so that means that the first easy step is just to realize that I can just write it up to a normalization constant, probably that I don't want to write, but that will be, say, proportional to. So let me just get out get rid of the Gaussian factors. And now I have the hardest piece to analyze, which is that I have a determinant of Hermite polynomials. Okay. So let's see how to play a bit with this determinant, and let's look at say an easy case, say the case n equals to 3 as an example. And let's try to write this determinant in the case n equals to 3. So what is this determinant? Well, in this case, the determinant of hk minus 1 xl is just the following. So I just need now to plug the expression of these guys that I gave here. Let me just plug it into this determinant, okay? So I will get 1, 1, 1. I will get 2x1, 2x2, 2x3, and then I will get 4x1 squared minus 2, and 4x2 squared minus 3. Okay, so this is an relatively easy to evaluate now, because you see I can manipulate it. For instance, I can just get rid of this minus 2 there by subtracting this, by multiplying this column by 2 and adding to it. Okay, so typically that means that I will just get this guy 1, 1, 1, 2x1, 2x2, 2x3, 4x1 squared, 4x2 squared, 4x3 squared. Right, but now I can easily get rid of this 2 there, this 4 there. So 4 times 2 is 8. Very nice. And eventually I just get this determinant 1, 1, 1, x1, x2, x3, x1 squared, x2 squared, x3 squared. But now you recognize an object that we have encountered before, because this is precisely a van der Monde determinant. Okay, and indeed you can easily, we have already seen it before, but basically this guy is just then proportional to x3 minus x2, x3 minus x1, x2 minus x1. Okay, so that's really nice now, because again, so this is this van der Monde determinant that we have seen before. Now, you guess what happens is that these manipulations that I have done here for n equals to 3, well, I could repeat it for any values of n by simply adding and multiplying, combining the different rows and columns of the determinant. And I will be always able to write this determinant as a van der Monde determinant, which we know how to evaluate then, and providing then this result. So that's quite nice, because this means that if I look at this psi 0, okay, could I ask you maybe to mute, because I can hear something which is a strange song. So this is just proportional to alpha square by 2 times the product okay. So you start to see some connection now with random matrices, I'm sure. But you have to remember that psi 0 is not the right observable, but instead what I want to look at is really the quantum joint PDF, the quantum probability, if you want. So that is the quantum joint probability density function of the positions of the fermions, and this is given by psi 0 squared modulus. And that's simply, so I just squared what I have upstairs. So this is exponential of minus alpha squared times the sum from I equals 1 to n of the xi squared. And now I have this van der Monde with a squared. And there is a global normalization factor that I will just write like this. Now, this is quite nice, right? Because this is precisely, this is extremely similar to the joint PDF of the eigenvalues of Gaussian random matrices that we have studied before, with a special value of beta, which turns out to be beta equals 2. Okay, so in other words, I mean, if I want to be, so if I just go back to this nice expression that we had before, that I showed you in the previous lectures, which is this joint distribution. So basically, you see that, so if I set beta equals 2, so that means that n lambda I squared is like alpha xi. Okay, so there is a one-to-one mapping, if you want, with the eigenvalues lambda i's of matrix belonging to GUE. Okay, so that's a quite nice application, if you want, or incarnation of random matrices in this fermion problem. And the mapping reads like that. I mean, that will be useful for us. Essentially, the mapping reads that alpha xi, which is indeed a dimensionless variable, identifies with square root of n times lambda I. Okay, so that means that there are lots of properties that we have seen before that we can now use directly to study our fermions. Now, it turns out that this is a rather special ensembles. I mean, if I look at GUE, this corresponds to beta equals 2, and it has very peculiar properties. I mean, the value, the special value beta equals 2 that I want to get into. I mean, I want to show you how this what is called determinantal structure I mean, can bring to the problem. And but the first thing, of course, that we can get easily is the density of fermions. Okay, so if I look at the density of fermions, I know that in the large n limit, I know that the lambda i's are distributed according to the Wigner semicircle. So it's clear that I will also get this the same Wigner semicircle for the xi's. There is, however, one thing that I need to keep in mind is that there is a square root of n here. Okay. So the support now for the density of the fermions. So let me put alpha equals 1 from now on. I mean, it's just that will be slightly more easy. Okay. So if I look at the density of fermions, well, we know what it will give. No, it will be again the Wigner semicircle. But now the spectrum, sorry, instead of being between minus square root of 2 and plus square root of 2, because of this square root of n factor here, then that will be, so that will be x. Let me call it rho n of x. So rho n of x, again, the way I define it here is just 1 over n. Okay, and I will have the Wigner semicircle, but the support again will be from square root of 2n, I mean between minus square root of 2n up to plus square root of 2n. Okay. So that's the first thing that we have for granted. Now, it turns out that for beta equals 2, we have much more, and we can explore all the correlation functions in this model in a relatively, in a very compact way, using the tools of determinantal point processes. So that's what I want to discuss now in a bit more detail. So these kind of processes actually plays a very important role in many problems in statistical physics and probability theory. And usually, so the first quantity which is central in this problem is called the kernel. And let me define it, and let me show you how it naturally enters into the problem. So there is a kind of very nice structure in the case beta equals.
Excuse me, one question.
Yes, please.
Like just like for the eigenvalues of GUE, can we not just scale the variables xi here so that we get a support from -√2 to +√2?
Sure. Yeah. Sure. Yeah. Of course. But still, in physics, in the physical problem, you have to keep in mind that the extent is actually over the square root of 2n.
Okay. So scaling is not allowed, is it? What you're saying?
No, you can scale, but if you are an experimentalist, if you have n fermions, you will not scale anything, right? It's not that you can choose the entries of the matrix, the entries of your matrix, and change the variance. Here, the fermions are whatever they are.
Okay, so you're saying that physically it doesn't make sense.
Yeah, exactly. Physically, it doesn't really make sense, but nevertheless, you can have in mind that theoretically, it is. You can just work with xi divided by square root of n, but you have to remind you that, or recall that the physical problem has really an extent which is proportional now to square root of n. Okay.
Oh, okay. Thank you.
So what is this kernel? Well, let me write again this guy here. So I had this psi0, which has this form, right? And therefore, psi0 modulo square is just the modulo square of that. Okay, so let's start with this expression, which in fact defines what a determinantal process is in general. So I will not make a course on determinantal point processes, but I just want to give you the flavor of the kind of techniques that we can have access to with that. So let's just write it this way. So I have this 1 over factorial n. And now I just write this way, determinant of KL. So Kn are running between 1 and n. So we have this first part, and then I have the same guy. Okay. So very good. So let me define now two matrices, which corresponds to that one and this one. So let me define the first matrix A with entries AKL, which are of the form phi L star xk, and similarly BKL, which is simply phi k of xl. Okay. So now this guy, this psi0 squared, you see, I can just write it as follows. This is just the determinant of the transpose of A times the determinant of B. Okay. Now this is again the determinant of A times the determinant of B, and that's again 1 over factorial n of the determinant of AB. Okay, so that's just very elementary linear algebra. But now let me rewrite this AB in a sort of interesting way. So if I just want to write the matrix element, so A and B are upstairs, right? So if I just write AB matrix elements KL, So what is that? Well, that, by definition, this is just the sum over M from 1 to n of A, K, M, B, M, L. Okay? And if I just plug these expressions there, I just have something which is just the sum from M equals 1 to n of phi M star of xk phi M of xl. And this is what I would want to call, well, what we usually call the kernel, okay? At this stage, it looks a bit formal, but you will see how useful it is. Okay, so that's what we call the kernel. So it's nice already to see that, in fact, the psi 0 squared has a simple determinantal expression, okay? So that means that, sorry, I can just rewrite the full joint distribution as 1 over factorial n times the determinant okay. So that's sort of nice, because that means that the joint distribution, you see, is actually fully specified by this matrix, okay? This is a matrix, or an operator, if you want, which is simply defined by this. Which in the case of harmonic oscillator is explicitly known, right? Because I can just enter the Hermite polynomials, and on top of that, the Hermite polynomials have nice properties, which makes that the kernel eventually has a very nice structure, which is called Christoffel-Darboux. I will not enter into these details, but just to say that it's quite useful. So, okay, now you might ask, okay, why is it interesting? Well, it turns out that if you look at this Kn, it satisfies a nice identity, and it turns out that the kernel is reproducible. So what does it mean? Well, it means essentially that it acts as a projector. So what in the sense of linear algebra. So let's look at this product. So let me just look at K and XZ and make the product K and ZY, and just now perform the integral over Z. Okay, so it's a kind of it's the equivalent of the product of two matrices, okay, but extended to operators here. So let's see what it gives. Let's just write it explicitly. Well, this will just be, so let's just expand. So this is just a sum over K from 1 to n, a sum over K prime from 1 to n, and let's just write this, what these Kns are, okay? So this is just phi K star of x, phi K of z, and then I will have phi K prime star of z, phi K prime of y, and now I will integrate this from minus infinity to plus infinity of dz. But now you have to remember that these guys, right, they are actually the eigenfunctions of Hermitian operators, okay? And that means that they are basically orthogonal. So that's the property here that I want to use, is that this integral over z will produce a delta kk prime. And eventually, it turns out, so it means that this is just the sum from k to n of phi k star x, phi k of y. And this is precisely Kn of xy. Okay, so that's what reproducible means here, is that we have this very nice identity. Great. So why is it interesting? Why is it important? Well, I just wanted to show you that because it turns out that if you have these reproducibility properties, which is quite crucial, in fact, then it turns out that the higher, also the correlation functions will have a very nice problem, the properties. Okay, Tridib asks, sorry, let me just take the, in what sense it is a point process? Okay, yeah, so it's a point process in the sense that the xi's are random variables, and these are the positions of points, if you want. And the probability density of this point is just given by something of that form.
So you mean all correlations then you could write down in terms of determinant. That's why it's a determinant of point?
Yeah, exactly. So that's the property that I want to come to, yes.
Ah, okay.
Yeah. But in general, okay, you could think that this defines a point process like that, okay? I mean, this defines the joint probability function of finding your particles or your points at given positions, say x1, x2, xn. And then you can ask what kind of structure do I have behind? And it turns out that here, because of these two things, namely that the psi0 squared can be written as a determinant here, and because of these reproducibility properties, I will not do all the details of the computations, but it turns out that all the correlation functions that I will define in a moment, then they actually take a determinantal form. Okay.
Thank you.
Okay. So the consequence of that indeed is that say that correlation functions that I will define in a minute. So let me introduce these correlation functions. So they are, I will define them small n now. Okay, so small n is different from capital N, and basically they are obtained by integrating. So I want to take the my joint distribution psi0. So I have, let me call it n here, n plus 1 xn. Oh, sorry, it's not very readable. So I have xn, and then I integrate out over xn plus 1 up to xn modulo squared. Okay, so I keep fixed the small n first variables, which are that one, and I integrate out over all the other ones. Okay, that's a quite natural definition of correlation functions, and that means that here I integrate over the xn plus 1 the xn, and in principle I integrate them over the full real line. Now, for some combinatorial reason, and also historical partly, so let me just write this better. There is a combinatorial factor here, which is just this is due to the fact that the measure is invariant under permutation of any of the xn's. Forget about that. So what is nice is that, so you see, so initially you start with a determinant, which is this guy, and then you start to integrate out larger and larger numbers of particles. Okay, so the capital N correlation function is just this determinant, fine. And then you start to integrate, for instance, the capital N minus 1 correlation function. So you want to integrate over xn, for instance. Now it turns out that, and then eventually over xn and xn minus 1, and then xn, xn minus 1, xn minus 2, etc., etc. Now it turns out that this determinantal structure that you have will persist upon integration. And it means, this means more precisely that these guys here will remain a determinant that you will build from your kernel, x, say, let's denote it k, xk, xl, but now the size of the determinant is small n. Okay, the same as here. So that's quite a remarkable property. This is, so that means that the correlation functions are determinantal, right? So that's the point. And that's what we call this process a determinantal point process. Okay. Great. So this is quite nice. In fact, for those of you who are more from condensed matter, this is somehow a consequence. I mean, you can view that as a consequence of the Wick theorem. Okay. I could tell more if you want, but just maybe a remark for those of you, again, who are more from the condensed matter community. You can also write this correlation function in a second quantized version, okay? So if you denote by, suppose that I have the ground state, this is my ground state. So one way to okay, so in second quantization form, okay, for those of you who don't know, I mean, forget about it, but this is just to connect this result to maybe more familiar ones that you have seen before. This is the annihilation operator at point y, this is a creation operator at point x, and kn of xy is simply this correlation function, okay? Psi dagger x, psi y, and you probably know that if I have a non-interacting fermion problems, then that means that in the second quantized form, the Hamiltonian is quadratic in terms of the creation and annihilation operators, and therefore you can apply the Wick theorem. So the determinantal structure is exactly similar to this, to the Wick theorem. It's really strictly equivalent. Okay. And somehow, in a way, this determinantal point structure that and the derivation that I tried to show you, I mean, it's not derivation, but would be more from the point of view of first quantization, if you want. Anyway, I want now to go to have more information and to get more information, to see what kind of information I can get from this nice determinantal structure. So there is a whole family of observables that we have already encountered and which are usually called whole probability. And it turns out that for determinantal point process, they have a very nice structure. So let me just, define what a whole probability is.
Gregory, one quick question.
Sure.
So, I mean, so you constructed the this kernel kxy using the, I guess, the basis wave functions, right, of the harmonic oscillator.
That's true. Yeah.
So, so in general, if I use like some other potential and just take this eigenstates and construct a different k, then it would define a new determinantal process.
Definitely. Yeah.
Okay. Okay.
So I have actually here, I chose the, I mean, I had in mind the harmonic oscillator because I chose you I mean, I wanted to show you the connection to RMT.
Right, yeah.
But indeed, I mean, that's a good point. In fact, any Hamiltonian, at least, yeah, any Hamiltonian which has a sufficiently large number of bound states to create a ground state, then indeed I will be able to construct this. So essentially, I will be always able to write something like that. That's what you are saying.
Okay.
where this psi k here are the eigenfunctions of my Hamiltonian.
Right. And then you just use orthonormality, right? So that
Yeah, exactly. Yeah, precisely. You see, I mean, what I used here is just the orthonormality.
Right. Yeah.
And because this property is crucial. But as you said, so in fact, determinantal point processes, in fact, were initially introduced, I mean, long time back, to study fermions in general. And then it was sort of renewed. I mean, the interest was renewed because it plays a very important role in some models of random matrices, and in particular in the GUE.
Okay.
Yeah, but that's quite nice because indeed, and that's also why we played a lot with these fermions, is that then you have access to a huge number of new determinantal point processes.
Right. Okay.
Yeah. Of course, there is some universality, and I will come back to that. But in general, you will have different point processes.
Gregory,
You'll discuss those later, is it?
I will discuss a little bit the question of universality.
Okay.
Gregory,
Touch upon this. Yeah.
yeah. This correlation function you have obtained, that is also same as basically the probability distribution of a smaller system, right?
Yes, indeed.
Yeah. So the correlation function, does it mean anything else also apart from that, or because
Some kind of, in a sense, in some renormalization group sense or something like that?
yeah, because I mean, I'm just trying to understand, because you have a bigger system of capital N,
Yeah.
and then you have integrated out some degrees of freedom. So what does it mean actually?
Yeah,
like
there is, however, one thing. It's not completely true because you still have the capital N here.
But this N, how does it appear? That capital N in
Yeah, the
case?
capital N, it enters into the kernel. Okay, so the sum here goes up to N.
Okay.
And small n is the size of your determinant. So it's not strictly speaking, it's not exactly, I mean, a simple size reduction.
Yeah.
Okay. So we want to, so the thing that we have, and we have already discussed many times, I mean, such problem what related to whole probability. So let's just illustrate it quickly. Let's look at the real line where my fermions live. And let's look at, let's define a certain interval, which I will call J. It could be a disjoint interval, but let's look at the simple one, okay? And essentially, so the whole probability is really the probability that, so if I denote Nj, I mean, basically what you would like to know, I mean, for this problem is the fluctuations of Ng, which are the number, which is, sorry, the number of fermions in this interval, okay? And the whole probability is typically the probability that Nj is equal to 0. And this is related, for instance, to the gap statistics that we have been studying. So what is the probability that I have no particles here? You can think of the whole probability, I mean, as being related to the statistics of X max. For instance, if you want X max to be less than this value, that means that you want to have no fermions on the right, on the whole real axis here, okay? So essentially, this is a very crucial, crucial property. Now, it turns out that for the determinantal point process, you have a nice expression for the generating function of this quantity here. So let me introduce it. So I will define, so I want to see it as a generating function. And this is just this guy. So this is definition at the moment. Okay, so that's this expectation value. So P is a real parameter. I prefer it to have positive in general. And that by definition, you see, is just the sum So I'm saying it's generating function because you can write it like this, right? It's just exponential of minus Pn, I'll say here, Pn, times the probability, sorry, that Nj is equal to N, okay? Fine, so that in that sense, this is really the generating function of these probabilities with a parameter which is exponential minus P. Now it turns out that for determinantal point process, this can be written, this quantity can be written explicitly in terms of what is called a determinant, a functional determinant or Fredholm determinant. I will define it in a minute. But you have an explicit expression. This is the determinant of identity minus 1 minus exponential minus P times Pj. So I have several things to define for you in a minute, but I will do it. Okay. So that's a very crucial relation. I need to introduce you several things. First, this guy is called a Fredholm determinant. So let me just suppose that I have the identity minus some operator k tilde. Okay, so that's a Fredholm determinant. That I constructed for some operator k tilde. So k tilde is like a matrix, but with continuous indices, if you want. Okay, so that's an operator k tilde of xy. Now, the way you define it is just a generalization of the determinant, but to a kind of infinite matrix. So the way you do that, you usually exponentiate it. So you say that it's exponential of log determinant, and then the log of the determinant, you know that it's a trace of the log of the determinant. And then you can just expand it, and that gives you an explicit formula, which I just write for you here. So this is just a sum over, sorry. So this is just the sum from m equals 1 to infinity of 1 over m times the trace of k tilde to the power m. That's a bit related to what 3D was asking the other day. But here, okay, here this is really, the sum is really infinite. Okay, so that's, maybe you are not all familiar with Fredholm determinant. I mean, don't worry. I mean, it's just to tell you that I give you a formula, so I want to explain what it is. But it's fairly explicit, okay? So now, so I have explained to you what is this guy here, okay? So this is my k tilde here, okay? This k tilde is actually this operator. This is just a number. Kn, we have seen what it is. Kn is just the kernel that we have seen before. Okay, so again, this is just this object. This is this guy. Now I need to tell you what this Pj is. Okay, so Pj is very simple. Pj is just a projectors, what we call projectors. So Pj of x, I will illustrate it, is just equal to 1 if x is in J, and 0 if x is not in J. So what it means precisely, you see in this formula, I need to compute the trace of k tilde to any powers, okay? So I will raise this guy to some power and take the trace. So let me just show you how it works with this projector here, just as an example. So I will need to compute the trace of this operator Pj k Kn Pj. So in general, you see, in general, this would be simply the integral over dx of Kn xx, but simply because I have this Pj, so that will be simply Pj of x. So that means that here,
Gregory, I missed something in that the previous equation.
yeah.
Yeah. So that no, the previous, yeah. So that from the first line to the second line, you are saying that it is a property of the determinant point process, or it is something you are going to show?
I will not show you it.
Okay, so you are saying that if expectation value of this exponential of minus p and j is given by this basically.
Yes. Yeah. Exactly. Yeah. Yeah.
Okay.
So that's okay. Should be clear. That's for determinant of point process.
So it's not coming from the second expression on the right hand side basically.
No. No. It's really a property, a very specific property. Okay. So DPP is, yeah, you're right. It was not very clear. Determinant of point process.
Okay.
So the statement is that one can show that this generating function can be written as this determinant.
Okay.
Now, these lines here are not any proof. They are just an explanation of what this formula is. Yeah.
Okay.
Okay. So again, I hope it was not too confusing what I said here, maybe a little bit. So I will just
Gregory, this okay,
yeah.
and oh, you're taking, okay, so Kn had two arguments x and y, but because of the trace, oh, that's the trace, is it? Okay.
Yes, exactly.
Yeah. Okay. Okay.
The trace fixes x, the two x here to be equal.
Okay. Okay. Right.
Okay. So that means that each of these, so eventually the effect of these pj's here is just to restrict all the integrals to be within the interval j. Okay, so that's what this guy means. So it's a quite general formula. In general, of course, it's pretty hard to manipulate. It can be evaluated numerically. I mean, nowadays there are some nice algorithms to evaluate this Fredholm determinant. But let me just show you one nice application of this formula.
So Gregory, so what was J? I didn't understand. So J was the interval?
Yeah, exactly. So J is just this interval.
Okay, okay, thanks.
So this holds for any interval, in fact. It could also be, I mean, several disjoint intervals or whatever. I mean, here it doesn't need to be connex.
Okay, thanks.
Connected, sorry. Okay, so one nice application is to the statistics of the rightmost fermion, or the rightmost or the largest eigenvalue. Okay. So indeed, there is one nice application. First application that you can see here is that if I really want to compute a whole probability, well, it's just like it really likes. I just need to take the limit p goes to infinity, because you see that if you look at this formula, and if you take p goes to infinity, well, on the right-hand side, the only term that will remain is the term n equals to 0, because all the other ones, I mean, they will decay very fast, exponentially. Okay. So that means that in the limit when p goes to infinity of this guy gives precisely the number of the probability that nj equal to 0. So that's just the whole probability. And you see that in the limit when p goes to infinity, this is quite simple because this is just this term that cancels. So that's the first observation. So the first observation is that in general, the probability, so the whole probability, oops, sorry, the whole probability you can just get it from the limit when p goes to infinity of this generating function. Fine. Now the second observation is that if you want to look at the probability, that x, so this is more specific to x max. So if you want that all the particles as, say, less than m, well, you see, this is just the probability that there is no particle in m plus infinity. In the interval m plus infinity. Okay. So that's a whole probability on this interval. And therefore, I can just use this formula that will tell me that this is just the Fredholm determinant of identity minus the projector on this interval m plus infinity times kn and times the same projector. So that's, let me just write it in words, I mean in formula instead. So that will be a Fredholm determinant of I minus the projector on m plus infinity kn times pm plus infinity. So that's really quite powerful formula, and that was somehow the starting point of the Tracy-Widom formula. Okay. So that tells really that this essentially with this kind of formula you can compute whatever you want regarding full counting statistics in your system. What is crucial, of course, is that you need to have a good knowledge of your kernel, okay? Because this is really you have seen that this is really the object that controls everything in your system. We have seen that it gives all the correlation functions, as here, and now you see that it also controls the full, the full counting statistics through this kind of formula, for instance. So it's clear that you would like to understand it, to have a precise knowledge of this kernel. And at this stage, we are somehow back to what we have seen before, which is that you remember that we have seen that there are actually two different regions in our system. One which is the bulk, and the other one which is the edge. And it turns out that if you look at the kernel, either in the bulk or at the edge, the properties of this kernel turned out to be extremely different. And that's what I want to discuss now. Okay, so I want to understand now. So I hope I convinced you that everything is contained in this kernel. And now I would like to understand how this kernel, what is the shape of this kernel in the large n limit. And for that, I will have to distinguish between the bulk and the edge. Okay?
So Gregory, so did you say that even the many interval distributions is also contained in a similar determinant form?
Absolutely. Yes. So
okay.
Yeah. So it's it's basically exactly the same formula. So
in fact, I could really then write down generating function of all these particles. So pi lambda I or xi. That multi-particle generating function would also have a Fredholm determinant.
Exactly. Yeah.
Okay.
Yeah, exactly. It's not completely obvious, but it's true.
Okay.
Yeah. And this is indeed contained in this. So this formula, indeed, it's quite remarkable. Okay, so there are some nice reviews on determinantal point processes. I will give you some references. They are mainly for mathematicians, but there is one by Borodin and there is another one by Johansson, which are quite nice. I mean, at least which are partly accessible for physicists. But okay, so now what I really want to understand is the large n limit of the kernel, because you see, if you want to analyze the large n limit of such a formula, for instance, n actually what is very nice in this kind of formula is that n only enters here. Okay, so that's so again, as we have seen, we will have pretty different forms if we are in the bulk or at the edge. Okay, so let's have a look at this. So we have seen that we have two scales. Okay, I mean we have understood that already from I discussed this before in the previous lecture, but essentially okay, let me just redo it. It will be faster just to. So again, we have this guy, and it's not very nice. So what we have seen is that, oh, sorry, oh, forget about it. Okay, basically we had the bulk. Okay, so again, we have the bulk. So here we need to it's a little bit different from what we have seen before for the following reason. If I look at the scales.
Can I ask a quick question?
Sorry?
No, a quick question, like this for the determinant point process, is it always semicircle, the density of this
No,
thing? Or
no, absolutely. Okay, so that's a good question. So I still have in mind here the harmonic potential.
Okay. So in general, one doesn't know what is the shape of.
In general, it's even. I mean, okay. In general, there is a formula which is given by the LDA, actually by the semi-classical approximation in the context of quantum mechanics, which is called the local density approximation. Okay, and okay, that's a good question. I didn't want to discuss it now, but maybe it's a good point nevertheless. So what Sanjib is asking is what happened if I have in general, if I have a single particle Hamiltonian, which is of that form. Okay. Then for large n, the density in the bulk, so the bulk density, so typically the Wigner semicircle, is given by semi-classical approximation, which is usually called either Thomas Fermi or local density approximation. Now, what it tells you is that the density rho of x, there is a normalization factor, but the dependence on x is relatively simple. It's just square root of mu minus v of x. Now, what is mu? Mu is just the Fermi energy. Okay, so that's the highest level, which is the highest energy level which is occupied in your system. And it's quite nice indeed that you see if you put v of x is equal to x squared in this formula, then indeed you recover the okay, you need to evaluate mu, but eventually you recover the Wigner semicircle. You see, it's quite nice actually. But it says also that, it says several things actually, but it says first that in general, the density will depend on x, on v of x, in a rather strong way. Of course, it will have a finite support because mu minus v of x has to be positive. So that means that you will have a support which is defined by v of x edge equal to mu, if you want.
The connection to random matrix is only for quadratic potential.
Yeah.
Okay.
Okay. There are some other ones, but there is a limited number of them.
Okay.
So in some sense, this formula is more general, and unfortunately, it does not apply to all the models in random matrix theory because they are not all of them coupled, related to fermions. But if you can find a relation with fermions, then this LDA gives you automatically, directly the density, which is usually a quite non-trivial things to compute in random matrices.
But Gregory, this formula is like in going to infinite. This is how accurate is it? I mean, like it's
okay. In general, it gives you the accurate in the sense that it works only in the bulk. So it's really it does not tell you anything really about the behavior at the edges, except that the density vanishes at these edges. But it's exact. I mean, it always gives you the correct large n limit, and that means that you can, in principle, have a 1/n, compute the 1/n corrections to that. Usually, it's quite accurate.
Okay.
If you're asking for more precise bounds, I think it's pretty sure that mathematicians have studied that. This is the kind of results that you would obtain when you do some kind of semi-classical expansion like WKB, for instance, in quantum mechanics.
Okay.
So it's relatively well. It's well established and well studied. So I'm sure that people have studied I don't have them in mind, but I'm sure people have studied the 1/n corrections to that. Although it gets more and more involved, of course. But the leading term formula is remarkably simple, right?
Right. Yeah.
So the point is that this LDA actually gives you more or less the correct, what you want in the bulk, okay? And you see that, so that means also that the global properties are pretty much will depend on v of x. This does not say anything about the behavior at the edges, okay? So that's one thing that I would like to discuss in a minute. So that's the other, and the same here. I have also the left edge. Okay, so I have these two regimes. There is one thing maybe I just close this discussion on general v of x by the following remark. Maybe I will come back to that later, but you see there is this square root behavior here. And that means that the way the density vanishes at the edge here is always a square root. Okay. And that sort of indicates that there would be some universality at the edge. That means that if you start to look at the local correlations at the edge, it should not depend too much on v of x. And in fact, one can show it does not. This is something that we have shown with Satya, Pierre Ledoussal, and David Dean. Mathematicians also have some, rigorous results on this line. But the universality mainly comes from the fact that you have this square root vanishing here. In fact, also in the bulk, so that means that, and that's what I want to discuss now, even in the bulk, inside the bulk, if you look at local correlations, it turns out that they are also typically universal. Okay, so let me just look at now the limiting form of the kernel, both in the bulk and then at the edge.
Hi, can I have one quick question?
Yes.
Is there any connection to matrix models for this arbitrary potentials? If not to Wigner, like some other correlated matrices, is there any connection for this distribution?
Okay, so in general, okay, there are some. There was some. Okay, so in the sense that there is no general. there is no general recipe if I give you a matrix model, how to compute, I mean, or whether there is or not a fermion model which is associated to that. Note also that the Gaussian case is extremely peculiar because it turns out that you start in a random matrix model, you have a V of M, which is M squared, so which is quadratic, and the corresponding potential in the quantum system is also quadratic. Okay, but in general, there is no reason why they should coincide. And in fact, the number of models for which the number of matrix models for which there is a fermion problems associated to it is relatively small. And in general, for a quantum model, so if you start from a quantum mechanics and you give me some V of X, then typically there won't be any matrix model related to that.
Okay, it's not simply V of M or something like that.
No,
distribution.
No. They are. It's in that sense the Gaussian ensemble is a bit misleading because it's really a strange coincidence. But in general, they are completely different.
Okay, thank you very much.
Okay. So yeah, so let's look at the kernel in the bulk. Okay. So again, here I will not show you any proof of that, but I just want to provide you some results. Okay. So it turns out that in the bulk, the kernel takes a scaling form. So if you look at k, n, x, and y. So really, I mean, because of the correlation in this model are relatively small somehow. I mean, weak in some sense, in the sense that if you want to really observe some non-trivial correlations between your particle, they need to be relatively close from each other. And that tells you that it takes a scaling form, which I denoted this way, x minus y divided by ln. So ln is the typical scale of correlations. And what is ln? So ln in this model, oh, okay, yes, I would need to tell you something. It's just related to the density. So it's just n of x. And I need to tell you, so this is relatively small. I mean, this quantity, okay, you don't know what is rho n of x, sorry. There is rho. This is just the density rho of x. And the sine function, the kernel, the sine, so this is the famous sine kernel. Maybe you have heard about it. And in this convention that I have, okay, there are some strange factors, but this is of that form. So morally, I mean, this is just sine z over z, okay? So that's the famous sine kernel, which, I mean, the pioneers of random matrices like Dyson, Meta, etc. I've studied at length. And this is a very important function and kernel, correlation kernel that enters. And this one is universal, in fact, in the sense that this regime here, so if you really look at the local scale, if you really look at local correlations in the bulk, then this ln here you see will not be universal. So ln will depend on the potential because rho of x does depend on it, but the form of the correlations is universal. Okay.
So this is not symmetric in x and y, is it? Can
yes, okay, it is actually, because this function actually is an even function. So
no, because this ln has only x, right?
Yeah, okay. You are right. You are right, but you have to have in mind that I should have written as a half of rho of x plus rho of y. That's a good question, but the way I presented here is not okay. It turns out that the scale on which I'm looking at is much smaller than the scale on which the density varies.
So you're putting rho of x and rho of y both same.
Yeah, exactly. So at this, exactly. So one really has to keep in mind that I am sort of looking at really what happens between 2 points, which are actually extremely close to each other. such that the density essentially does not vary. And in fact, a signature of this is also the fact that you see you have a, here you have only a dependence on x minus y. That means that your kernel is translationally invariant in that sense. So that means that, of course, this can only be true on a very short scale, right? Because as soon as you start to see the variation of the potential, then at that stage you lose the translational invariance. So that says indeed that this correlations and this regime is really when you are considering 2 points which are very small compared to the scale of variation of the potential. But on that scale, and this is not a big surprise, but on that scale, these correlations are universal and they are described by the famous sine kernel. Okay. Now let's see what happens at the edge. The edge, of course, is supposed to be quite different. I mean, here you see that there is immediately a problem in this formula because at the edge, rho of x becomes 0. Okay, so this formula cannot hold, obviously. I mean, at least ln becomes very pathological. And it turns out that indeed, when you start if you now consider 2 points close to the edge, well, of course, they start to see really the variation of the potential, and you lose also the translational invariance. So that means that the kernel then is not anymore translationally invariant, and it takes the scaling form that I want to give you to discuss now. Okay, so I will just look at the things this way. So I want to look at kn xy. So what I'm saying now is that this is a scaling function, kai for airy, as you can imagine. And this is, so x edge, what I call xe is the edge divided by wn. So xe is the edge, wn is the width. Okay, so let me just define you a bit more precisely what I have in mind. So this is what I call x edge. And this is the width of the edge. Okay. So for the harmonic oscillator, and there is a factor, okay, it has to be. So this is the scaling form that it takes. So again, I should say that for the harmonic oscillator, one has that x edge is basically square root of 2n, and wn. Okay, you remember that in the random matrix context, maybe you remember that I was estimating the width of the fluctuations, and the width of the fluctuations in the eigenvalue language was n to the power minus 2/3. But you have to remember that for the random matrices, the support was between minus square root of 2 and square root of 2. For the fermions, you remember that there is a square root of n additional, right, in between the two. So the wn actually is not n to the power minus 2/3, but this is n to the power minus 2/3 plus half. And this is wn, so this means that this is n to the power minus 1/6. This is just due to the, but that's the same exponent. The origin of the exponent is, of course, is the same. Now the question is, what is this nice function here? What is this k-airy? Well, this is called the airy kernel, the famous, I mean, which became quite famous since Tressier and Widom, I should say. Even, in fact, I should say Peter Forrester also, because he was somehow the first one to derive this airy form. But this k-airy, let me give it in terms of two variables, x and y. It has this nice form in terms of the airy function. area of x, area prime of y minus area prime of x, area of y divided by x minus y. Now, it turns out that it has an alternative representation which is quite useful, and I just give it because it will be useful for us next time. Okay, so that's again the area function. Okay. The area function has enjoys a lots of very nice properties, and among them there is this nice identity. So as I said, you see, so this is called the area kernel. Okay. So why is it interesting? Well, I mean, essentially with that, you can compute many things that you want, and in particular, and I guess I will finish with that. In particular, you could now compute this probability distribution here for x max. Okay, so if you insist on computing that, you can now analyze this and use you can use this formula and use the fact that basically, if you want to look at the typical distribution, at least of the largest eigenvalue, then you will need to look at m very close to the edge. And that means that you will be able to use the asymptotic formula of Kn that I just gave for you. That is this area kernel. So one application of that, of the whole setup, of the whole formalism, that so if you assemble all the different results that I have shown for you today, is that we can now write the probability that x max is less than m. Well, it turns out that in the large n limit, okay, it takes a scaling form, which I write in terms of this f2 function. And this is a function of the following argument, m minus x edge divided by wn. And this is the only reasonable variable that you can think of at the edge. And this area 2, I mean, this f2 function, f2 of s, while this f2 of s is a Fredholm determinant of 1 minus the projector, which depend on s only here, times the area kernel that we have seen, times ps. Okay, so that's actually the Tracy-Widom distribution.
So connection with this one to this Panlavik solution of this Panlavik equation is obvious, or it's? Yeah.
So this I will leave it as an exercise. Okay. So this actually was I mean is far from trivial, and that I just wanted to comment on that. So this was really the work actually of Tracy and Widom, because this formula was known. I mean, it's essentially the formula that you can easily write from the theory of determinantal point process, and the true input of Tracy and Widom was to show that by analyzing this, I mean, rewriting this Fredholm determinant in terms of Painlevé function, I mean, was really their main result, in fact. Okay, so I will probably finish just with that. And that's with Painlevé 2 equation. Okay, so this is actually something quite non-trivial, and again, this was really the main achievement of Tracy Widom in their paper from '94. And then their method actually can be extended. I don't know any easy way to do that. We have used these methods in various papers, but it's quite involved actually. There is
So
no simple way.
numerically, one can still get the distribution from this form, I guess, right? Or
say it again.
No. If you want to get the now numerically the distribution,
Yeah.
One can probably still get it from this determinant formula.
Yes,
or...
that's true. So yeah, so at the time of Tracy and Widom, actually, I mean, I think the methods, I mean, were not very well developed, and people were quite happy to have this expression in terms of Pain-Levé-2, which were sort of easier. But since then, there are very powerful methods. I mean, in particular, developed by Bornemann in Munich, which actually allows to evaluate this Fredholm determinant with a very high precision.
So is there any advantage of the other formula, or because the other formula also you have to still do it numerically, right?
Yeah. So the other formula actually, so the other formula is actually extremely useful to analyze the asymptotic behaviors of F2 of S. So if you remember, so basically there is it's a bit in the right tail. So if you want to study the right tail of this object. It's quite simple actually to do that, because basically you can use if you use the trace expansion, basically what happens when S is very large, P of S actually constrains the interval of integration to be very small between S and plus infinity. So basically you can just skip the first term and analyze the trace of this guy. So you just need to analyze the Airy function, and that's the tail, which is exponential of minus S to the power 3/2. But the other tail, which is this exponential minus modulus of S to the cube, actually it's extremely difficult to get out from that. I think it has been done by Baik or some specialists of Riemann-Hilbert techniques. But on the other hand, if you look at the Pain-Levé formulation, it's almost immediate.
Yeah.
So that's really the one of the advantage of these things. Yeah.
Oh, okay.
And again, also it came out of a bit of a surprise. I mean, because this Pain-Levé function actually has popped up already in the 50s or 60s in the context of integrable system in the Jimbo, Miwa, the Japanese school. And so people were quite a bit surprised, I mean, to see that this Pain-Levé equation was entering into the realm of random matrices, and then suddenly connected to some real system. I mean, real, like KPZ, like although up to now it had been okay. There were some applications of Pain-Levé functions in the context of Ising models, but this was really one nice breakthrough. So yes, I mean, I guess I will stop here. I mean, there would be still many other things to say about this determinantal point process. I will essentially stop here. So in the sense that next time, what I want to discuss is basically what happens at finite temperature. Okay. So here you see what is nice is that with these fermions, they provide a very nice application of RMT. And somehow they also provide maybe one of the simplest example where the Tracy-Widom distribution could be observed experimentally. I mean, people are start to think about that. And so, for instance, there are some groups, I mean, who are really able to. They have developed these very nice Fermi microscopes, which really allows to take some snapshots of the Fermi cloud, and then you can think of starting to make statistics out of that. And then so that opens hopefully a nice applications. So next time I will move to finite temperature, and I will actually uncover again a very nice connection with KPZ, but with the KPZ at finite time, not only in the large time limit, but I will show actually a very nice connection between these fermions at finite temperature and the KPZ equation at finite time. And yeah, that will cover. So I think it will take probably half of the next lecture. and then I will start to talk about this non-intersecting Brownian path, which turns out to be related to fermions and random matrices. So I think it will sort of close the loop. So that's the plan for the next lectures.
Okay. So this connection to KPG is through the Panlovi equation or through this other formula?
Yeah, it's really, it will come out, it actually comes from a formula which is more of that type, more of the Fredholm determinant type.
Okay.
Yeah.
So Gregory, I had one question. So
Yes.
it's about the generating function for this gap.
Right.
So it is for the gap, but you say that there would be a similar determinant formula if I also look for generating function for positions of the particles, right? Or the densities.
Yes, for the densities, yes, for the densities you can have relatively explicit generating function formulas. That's
yeah. So my question is probably a bit vague. So what I was asking, so now given this generating function, you are doing it all at a microscopic like scale. But then if you could do some coarse graining, does the coarse graining would also translate into coarse graining of the kernel? I don't know if I'm making the question precise.
No, I'm not sure I understand what you mean.
So you see, when you define the generating function, it is the generating function of all these positions of the particles. So it's like you're looking at small intervals and whether there's a particle or not.
Okay.
But then you could, in the interacting particle system, we often talk about this coarse grain density. So we don't look at a small interval, but increase the interval little by little. So that's where all these hydrodynamics and things do. So my question was that, is the coarse graining, if one does it translate into something in the kernel?
For the fermions, yes.
Probably.
Hydrodynamic description for the fermions. I don't know, actually. That's a good question, yeah. At least this has not been done. I mean, I don't think that people have thought too much along this line.
Okay.
But that's true. In principle, this could maybe be a way to do that. Yes, I agree. Yeah, but the answer is definitely that people have not done that, as far as I know.
Okay, thanks.
I guess
I just if there is no more, I have just one more question. So
Please.
this Fredholm determinants also, if I remember correctly, it appears in some kind of this integral equations. Do you think there is some connection of these Fredholm determinants that's appearing here to those kind of integral equations?
Yes. So okay. I mean, indeed.
So it's, you know,
So it was actually for the sine kernel, for instance, people have studied that. People have been interested, for instance, in the, yeah, okay, this is connected to that if you want. You see, when you want to compute some Fredholm determinant, you have this trace expansion.
yes.
Okay, now the trace expansion, okay, there are various ways of seeing it, but one way is, I mean, of course, if you know explicitly the eigenvalues of this operator, then you are almost done, right? So this is, I mean, this is one way that has been explored, at least quite a bit for the sine kernel. So people have really studied the integral equation associated to that kernel, and more precisely the eigenvalues and eigenfunctions of this, I mean, of this kind of integral equations, to have or to obtain information on the behavior of the eigenvalues of this operator. This is easy to do, I mean, sort of easy to do for the, I mean, at least it's a quite convenient way to proceed for the sine kernel, because the sine kernel, you see, is translationally invariant. And there are some nice method to do that. I mean, it's a kind of Toeplitz operator, if you want, right? It's like a Toeplitz matrix, but it's a Toeplitz operator. And then you have techniques to analyze the eigenvalues of such operators. And if you look at the papers by Mehta, for instance, the papers from the 60s of Mehta, he has actually explored quite, he was not alone, but he has been exploring quite a bit this line that you are saying. For the array kernel, it's much more complicated because you don't have this, I mean, the integral equation that you get is not of the Toeplitz form because of the fact that you don't have the translational invariance. This has been done, but I think much less. This has been done little bit in the, again, by mathematicians in the Riemann-Hilbert community. Tom Bottner, for instance, this kind of mathematicians have explored a bit the this line to again try to extract the eigenvalues of this operator.
Okay. Okay.
That's all I can say.
Okay. Thanks.
Yeah, there's no more questions, so I guess we stop here for today, and then